Hey guys, it's Trey Hughes, the Science Guru here, coming to you today with another video, this time on the topic of atoms. And it's kind of going to be like an introduction to chemistry as well, but I'll make a second part that's specifically for the introduction of chemistry. But it will have a lot of information from this atoms video as well. So it won't hurt to have a video specifically on atoms. And the first three things that we are going to talk about today are three contributions to what we now understand about atoms today. So the first is atomism, and it was a theory that was proposed by a Greek philosopher named Democritus, and he was one of the earliest atomists that began acknowledging the existence of atoms with his theory called atomism, which basically states that all matter is made up of indivisible particles called atoms, but we now call them atoms based from John Dalton's atomic theory that says that atoms of elements cannot be divided and that each element has its own identical atoms which make them easily distinguished from others. And last is the Bohr model, which was proposed by Niels Bohr, and he was a Danish physicist that created a depiction of an atom with electron shells. And it's this depiction that is very important in chemistry, especially in general chemistry when you're first learning about atoms and reactions and just elements and pretty much everything that has to deal with chemistry. When you're at that step, you learn that the shells from the Bohr model is what cause reactions to happen. The outer shells of atoms interacting with each other and sharing electrons or donating and stealing electrons between outer shells of two atoms. That is what makes reactions possible. And next, we're going to talk about three more scientists and their go forward experiment that they performed. We have Ernest Rutherford, Hans Geiger, and Ernest Marsden, and they conducted an experiment where they shot alpha particles at a thin sheet of gold foil, and alpha particles have a positive charge, and gold foil also has a positive charge. And so you may already know that like charges repels and opposite charges attract. Even it's made from watching TV or something, it's always like a chemistry thing that says opposites attract. So this is important here to understand that. And so what you may already predict to happen with that background knowledge is that the positive charged alpha particles is not going to mix or go well with the positive charge of the gold foil, but it's important to note that not all of the gold is positively charged. It's only the nucleus, which is the center of the atom itself. That's the only positive charge as far as the entire atom is concerned. So the shells or the electron cloud that surrounds that has a net negative charge because of the electrons. And so that's important to note as well. And so in figure B, you have two different drawings or pictures. You have the circle at the top, and you see the black lines going straight through. That is what they expected to happen with the gold foil and the alpha particles. They expected the particles to go directly through, but however, it was more so like the bottom picture in which you had some parts of the rays of the particles that actually went off to the back or even to the side within a certain distance. And so this allowed them to determine the size of the nucleus because they was able to say, okay, all of these went straight through, but however, in between here and here, nothing was able to go straight through. And so this must be where that light charge is interacting with each other and just not Okay, not so much interacting, but this is where the light charges meet and repel each other, basically. And so that's how the size of the nucleus was determined. And here was just a basic anatomy of an atom. All atoms are made with this basic anatomy. Now, the number of electrons or the size of the nucleus will vary from atom to atom, but they all have these basic components. And so, if we go from the inside out, then we'll start with the nucleus. Similar to like in biology when you first learn about cells and you have a cell and in the center of the cell is the nucleus. That's similar to the orientation of an atom. The nucleus is held in the center of the atom. Next you have electrons, and here the purple and the gold circles represents electrons, which I abbreviate with an E and a minus sign. Both of these are electrons. However, they are different um, electrons per se, because one is in the first shell, and that would be the first shell. And remember, we get these shells from the Bohr model, and this would be the second shell. And so in this case, the electrons that would cause reactions are the gold ones because they are in the second shell. And for this atom, it has only two shells, so the second shell in this case will be the outer shell. Whatever the last shell or the outermost shell is, it's called the outer shell, or also the outermost shell. And so if we then look at the green part, this is important as well. This is going to be called the electron cloud. The electron cloud is the space in which the electrons move around the nucleus. It's important to note that they do not move within a line such as depicted by the Bohr model. The Bohr model only acknowledges the existence of different shells. It doesn't trace the movement that the electrons make. They're going in their own directions and they don't follow a specific path per se. So the two gold electrons you see here will go in their own direction, and the two purple electrons have their own path that they are following as well. And here's just another drawing of the Bohr model for the magnesium atom. And as you see here, you have the electron shells and you have the nucleus. The nucleus has 12p, which stands for 12 protons, and you see 12N, which stands for 12 neutrons. And every atom has a nucleus, but not every atom has the same components in their nucleus. For example, the hydrogen atom has one proton but no neutrons, and it's the only atom that has no neutrons. But it goes to show that not every atom has the exact material in their nucleus. And so here is the nucleus. Here is the first shell, the second shell, and the third shell. So in this case, the third shell is the outer shell. And if you count the number of electrons from the first shell to the third shell, you'll see 2 in the first shell. And that's important because the first shell can only hold 2 electrons. And in the second shell, you see 2 right here, 2 right here, and 2 right there. And so if you're referring to the second shell by itself. Oh, and we have two right here. I was wondering where it was. So if you are referring to the second shell only, then you see 8 electrons total. 2, 4, 6, 8. And it's important because the second shell can only hold up to 8 electrons. And in the third shell, if you count the number of electrons, you only see one right here and one right there. And so there's only 2 electrons for the third shell. And so if we do the math right quick, we have 2 electrons in the first shell, and we have 8 electrons in the second shell. And then we have 2 electrons in the third shell. And so if we add these numbers up, then we get 12 electrons total. And since this atom, we can call this neutral because the number of protons, neutrons, and electrons are all equal. And so it's like overall everything is balancing out. However, you will have some atoms, especially metal atoms, that have like a positive charge or a negative charge on them. That's because of either the loss or the addition of electrons, and never the loss or the addition of protons, because the number of protons for an atom will not vary. So a magnesium atom will always have 12 protons. But in some instances, for the hydrogen atom, you may have a different number of neutrons as opposed to a different number of protons. So the number of protons will never change, but number of neutrons can change, and the number of electrons will change when you have any type of reaction. Okay, next we'll discuss the uniqueness of atoms. And I kind of just hinted about this. Every atom have a specific number of protons. Okay, so because atoms have a specific number of protons, we can classify or identify them based on that property. So a hydrogen atom will always have 1 proton. A helium atom will always have 2 protons. And for example, a fluorine atom will always have 9 protons. And if you look at these 3 different pictures, you see like 3 different drawings or representations of what an atom looks like. So for the fluorine atom, you don't see any protons or neutrons within the nucleus here. You just see the F drawn in the middle of the circle. Chemical symbols are also specific for each element. So fluorine is the only atom that has the chemical symbol of F. And if you look at the hydrogen atom, it's no drawing of a chemical symbol. It's only the number of protons. And we know that 1 proton is going to always be a hydrogen atom. And same thing with the helium atom. If we look at the number of protons, it's only 2. And so we know that it's always going to be a helium atom. So you can determine what atom is given to you if you're looking at it during the test or on a piece of paper or something when you're doing homework, by either the number of protons that they give you in the center or by the chemical symbol that they give you in the center. But the common thing between either having a symbol or the number of protons is it represents what the nucleus is. And of course, you always have the electrons orbiting around the nucleus as well, no matter what type of drawing. Now, you may be familiar the Lewis dot structure, in which you don't have any shells. You just draw the number of electrons that is present in the outermost shell. And next, we're going to talk about how the number of neutrons of an atom can vary. So, if an atom is capable of possessing a different number of neutrons, then the varied versions of the atoms are considered isotopes of the original atom. And I spoke briefly earlier about the hydrogen atom and how you can change the number of neutrons in it, but it'll still be a hydrogen atom because all of them have one proton. Well, it's the same thing with an carbon isotope, and so natural or like the normal carbon that you'll see on the periodic table is it has 6 protons and 6 neutrons, and we call this carbon 12. Um, and it's the 12th element in order if you're looking on the periodic table. However, carbon can have 7 neutrons in its nucleus as well, but it's gonna always remain with 6 protons. That's how we identify it as a carbon atom. And so in this case, you just add the number of protons plus the number of neutrons, and 6 plus 7 gives you 13. And since we know it's carbon because it has 6 protons already, we call this isotope carbon 13. And for carbon 14, it has again 6 protons, but in this case, it has 8 neutrons. And so 6 plus 8 gives you the 14. And since it has 6 protons in its nucleus, it is considered carbon. So when you put the two together, it is carbon 14. And all the last two are isotopes of the carbon atom, which is the first drawing here. Okay, next is the periodic table of elements. This is very important. You'll see this in every chemistry class and maybe even some biology classrooms, and they're almost always in the back of a science textbook, and you can get it online as well. It's very easy to find. However, the periodic table has a lot of trends as we look at it, and I'll make a separate video for some of the important trends and how to identify atoms based on the type of trends that they have. But these are all the known elements so far. The smallest atom is the hydrogen atom, and as you see here at the top left hand, it is number 1. And the size of an atom increases from left to right and then up to down, top to bottom. And so if we want to look at the first 3 elements or atoms and increase in size, we'll note that hydrogen is first, and then if we come over here, helium is second, and then if we go down to the second row, we see that lithium is third. And so you read the periodic table from left to right, then top to bottom, and that'll give you the increase in size accurately. The first trend that I want to talk about, or the first step to reading a periodic table, is going to be knowing the difference between a column and a row. So if you see here, a row goes from left to right, and a column goes up and down. And so hydrogen is in row 1 because it's the first row that's going from left to right. But it is also in column 1 because it is in the first column that's going up and down. Helium, however, it is also in row 1 because it's at the end of what's going left to right at the top. However, it is in column 18 because it is the 18th column. And so a column is also called a family or a group. Um, in terms of chemistry and the periodic table, those three words mean the same thing and they will always be used. I wish I could say one professor or one person just sticks to saying, okay, column, or they might stick to group or even family, but no, we use the three very freely, so don't let that trick you up. But however, we kind of stick with row with just being row. Okay, so if you look here at the top, you can see this box. And the box will tell you the atomic number, and the atomic number is also the number of protons for that specific element or atom. So, if we want to break down the sodium atom, the atomic number for sodium is 11, and the number of protons that sodium has is also 11. And so that's an important trend as well when you're beginning either general chemistry or just high school chemistry, is to know that the number of protons and the atomic number are equal. And so they're always going to be the same. Even if you have an isotope, the number of protons will not change. So that atomic number will always represent how many protons that element or its isotopes have. And so let's move on. Let's jump one row down to potassium, okay, and just describe it with what we've discussed so far. So potassium has the atomic number of 19. So that means it also has 19 protons within its nucleus. And remember, the nucleus is the center of the atom with electrons orbiting around it. If we look to the side, we see a 4 drawn next to potassium. And we know that left to right is a row. And so in this case, it is in row 4. However, it is in column or group 1 because it's in the first vertical group. Okay, and so if we look here in the center, then we see the number in greens that I circle as, for example, over boron, which has the atomic number of 5. So if we look at the green number right there, that tells you the number of valence electrons. However, when you get to double digits, it's always going to be the last number that tells you the number of valence electrons. And valence electrons are the number of electrons in the outermost shell. And so it's important to remember what we talked about in the beginning of the video because we're just adding on to it. So remember, with the Bohr model, you had more than one shell, possibly around certain atoms, and that last shell is called the outermost shell. And so valence electrons tell you the number of electrons within that specific shell. And so we know it's the number of electrons within that shell because valence is for the outermost shell. And the in the blue here you see electron shell formula, and this tells you how many electrons will be within each shell. And so that formula is 2n squared, and n gives you the shell number. I've never had to use this formula in general chemistry or high school chemistry, but it's a neat trick to tell you how many electrons are present in each shell. Usually, your teachers won't require you to know how many electrons there are in each shell past the first two shells. It's important to know that the first two shells can only hold up to two electrons, and the second shell can only hold up to 8 electrons. After that, the professor or the teacher might not require you to know how many the third or fourth or fifth shell electrons can hold. Um, and also, if you look here in the center, in between group 3 all the way over to group 12, you will notice there is no green circle at the top, and that's because the number of valence electrons can change within these group of elements because they are metals. And so we cannot say, for example, with the hydrogen atom, oh, it's always going to have one valence electron. You cannot do the same thing for these metals. And so we typically do not discuss how many valence electrons these atoms in the middle have, specifically because they always vary and is usually more than one number of valence electrons. So it might have a positive charge or a negative charge for the same atom depending on the type of reaction. So we cannot just give one of these elements a set number of valence electrons, because in one case it might be correct and in the next case it might be wrong. So with that trick is usually only for the first and second family, and then for groups 13 through 18. And remember, when you get to the double digits, you look at the last number to tell you how many valence electrons those atoms have. And so if we go all the way over to group 18, we see a specific type of atoms, and these are called your noble gases, and they are non-reactant because they have a complete outermost shell. And remember I said the outermost shell and those electrons are where reactions take place and they are the cause of chemical reactions. Well, that's only if the shell isn't full, and so in that case the atom might steal an electron from a different atom, or it might give away an electron to another atom in order to be stable. However, for these noble gases, they do not need to steal or donate electrons because their outermost shell is full by nature. And so these are typically not reactant, such as the hydrogen atom or the fluorine atom, per se. Okay, if we look here, we can see that atoms can join together or form a bond, and create molecules by sharing or donating electrons, similar to what I was just saying about the hydrogen atom or the fluorine atom. So an atom is a single atom. However, a molecule or a compound is a combination of multiple atoms. And so, for example, if you look at silicon, it is a single atom in this depiction. However, when you look at hydrogen gas, which is H2, that formula, it is a compound of multiple atoms. And in this case, it has the same atoms, two hydrogen atoms, but you can get combinations with different atoms, such as water, which is H2O, which has two hydrogen atoms and one oxygen atom, and that is also considered a compound because it has more than one atom. And here's a depiction of that. And so in this case, you have, like I said, one oxygen atom and two hydrogen atoms, and they form a bond in which electrons are being shared. It's a covalent bond because electrons are being shared, so That's where the word covalent comes into play, and it's a little vocabulary word that means a lot in chemistry. And I believe I talk about that within the next slide or two. And so that's just the difference between an atom and a compound. And so when we start talking about the types of bonds, we have to keep in mind that there are different types of bonds, no matter if the two atoms that are joined together are the same or different. And so if electrons are shared, then we have a covalent bond. For example, electrons are shared equally, then it's a non-polar covalent bond. So you have a covalent bond, but then you have a subcategory for types of covalent bonds. And in this case, if the sharing or the pooling of electrons are equal, then it's a non-polar covalent bond. Such as with the hydrogen gas, the electrons are being shared in between two hydrogen atoms, but since the atoms are the same, they have the same amount of pull on those electrons, so it's a non-polar covalent bond. When electrons are not shared equally, then that results in a polar covalent bond. And in the case of water, keep in mind I said that it is a covalent bond, but the specific type of covalent bond would be a polar covalent bond because you have one oxygen atom, which is huge compared to the size of an hydrogen atom, because it has way more protons and neutrons within its nucleus as opposed to the one single proton in the nucleus of an hydrogen atom. And electrons, they do have a mass, but for atoms, they are the same size. And so the atoms don't really contribute to the size of the atom. I'm sorry. The electrons do not really contribute to the size of the atoms. They're just more so telling what type of bond it is and determining what type of reaction has taken place or can take place. And so with non-covalent bonds, electrons are shared but not equally. So in the case of water, the electrons will be closer to the oxygen atom, and they'll spend more of their time circling the oxygen atom as opposed to the hydrogen atom. It'll have a weaker pull on those electrons, and the electrons will spend less time circling or orbiting the two hydrogen atoms. If electrons are donated or transferred, that results in an ionic bond. And here is a very common reaction and a product that everybody knows and probably has in their kitchen, and it is table salt, which is known as sodium chloride. It's a type of salt. You have many types of salt, but this is a famous one that a lot of people learn about and can think about off the top of their head. So you have sodium chloride, in which sodium has 3 electron shells and 1 valence electron, and chlorine has 3 electron shells and 7 valence electrons. And so the golden number in terms of shells is 8. And so in this case, it's like a give and take, and you have to see which one can afford to give and which one can afford to take. And so sodium only has 1 valence electrons, and what's the odds of it gaining 7 more electrons from atoms is very impossible. So in that case, it would donate its 1 valence electron to a different atom, resulting in 8 valence electrons technically, because it only has the remaining electrons in its second shell, which was full from the jump anyways. That's why it was 1 valence electrons in the third shell, because the second is already full. And so if you get rid of the 1 valence electron in the beginning, you're left with 7. You're left with 8 in the end for that sodium atom, because it donated that 1 electron. However, chlorine has 7 valence electrons already, and it only needs 1 if it's going to get to 8. And so it's very impossible for the chlorine atom to just donate all 7 electrons in order to do what the sodium atom did. The chlorine atom will instead steal 1 electron to complete its shell because it only needs 1, so it will not donate or give away any of its electrons. And so where does chlorine for this reaction get its 1 needed electron? It gets it from the sodium atom. And so these two form a bond together until they're put in water, then they disassociate. But they form a bond called an ionic bond because electrons are donated and transferred from one atom to another. And that sums it up for this general view of atoms for this video. And this is Cheryl, the Science Guru, and